A familiar scene in modern software. Traffic spikes, the checkout page hangs, and support teams start getting messages. Dashboards show something is off, but the cause is murky. Is it the database? The network? A recent deploy? Guessing wastes time, and in a high-stakes moment, minutes matter. Observability is the practice of understanding a system that can't be fully predicted by studying the signals it emits. Instead of poking around blind, the system describes itself through data that reflects what's happening inside. Here's the difference from the usual baseline of monitoring. Monitoring watches a handful of known metrics and alarms when they cross set thresholds. It's a smoke detector, useful for known risks. Observability is more like having a complete forensic kit ready, even for weird failures no one anticipated. It's built for unknown unknowns, the odd combinations of events that only show up in production. Why care? Because software now runs as a web of services, APIs calling other APIs, containers scheduled across clusters, third-party systems in the loop. When something slows down, the blast radius can cross multiple teams and technologies. Observability shrinks the what's going on phase from hours to minutes. That translates to fewer lost orders, happier users, and less stress for the people on call. A helpful mental picture ties the pieces together. Think of observability like a car's dashboard, black box recorder, and GPS route history working as a set. The dashboard gauges, speed, RPM, fuel, are like metrics that show high-level trends. The black box that records detailed events and errors is like logs. And the GPS track that maps the exact path taken through traffic is like traces. Each one tells a different part of the story, and together they explain both the big picture and the specifics. So pause on that for a moment. The dashboard, the black box, and the GPS aren't competing ideas. They complement each other. Software needs the same trio. Metrics are numbers tracked over time. Think of average request latency, error rate, CPU, memory, queue length. They are efficient, compact, and perfect for spotting trends. A single time series can summarize millions of events. That's why alerting generally runs on metrics. If the 95th percentile response time, often shown as P95, jumps from 200 milliseconds to 2 seconds, a metric alert can fire within minutes. Logs are records of discrete events with timestamps. They might say order created, card declined, or DB connection pool exhausted. Logs can be plain text or structured fields like event error, user id 123, order id 456. They excel at context. When a span of code throws an exception, the log can capture the error message, the parameters, and a bit of surrounding state. Traces show the path a single request takes across services. When the place order button gets clicked, that user request travels from a front end to a gateway, to payments, to inventory, to a database, and back. A trace ties those hops into one continuous story, with timestamps for each leg. That story is constructed from spans. A span is a timed unit of work, the call inventory service span, the query payments DB span. Each span records start time, duration, and metadata like which service handled it. Spans share a trace ID so they can be stitched together. What matters here is how these three signals align. Metrics make it efficient to notice something changed. Traces make it possible to pinpoint where in the request path the change lives. Logs make it possible to understand why that spot misbehaved. So the simple version is, alert on metrics, find the location with traces, explain with logs. Under the hood, this requires instrumentation, teaching code and infrastructure to emit these signals. Libraries and agents add small hooks into services so they record spans and metrics and write useful logs. An open standard called OpenTelemetry helps generate compatible data across languages and tools. So telemetry from a Node.js service and a Go service can be correlated in one place. There's a subtle but powerful mechanism that makes traces possible: context propagation. When a request enters the system, it gets a unique trace ID. That ID is passed along as the request calls other services, often through HTTP headers. Each service creates its own span and tags it with the same trace ID. A backend platform then assembles those spans into an end-to-end view. It's remarkable that a tiny identifier can link dozens of moving parts into a coherent narrative. Collecting signals is only the first step. They need to be aggregated and correlated. Metrics are rolled into time series. Logs get indexed for search. Traces are connected by shared IDs. The payoff is that a spike in a metric can be tied to a specific pattern in traces, which then leads to the exact logs at the bottleneck. That correlation unlocks speed. Consider a real example: an e-commerce system with a front end, A payment service and an inventory service sees checkout latency jump to 5 seconds from 200 milliseconds during peak traffic, alerting triggers on P95 latency above 2 seconds and error rate rising to 10%. The operations team opens the trace viewer and filters for slow checkouts. One trace stands out. Most time is spent inside the payment service. Drilling in shows a long wait while calling inventory. At the inventory span, linked logs reveal DB connection pool exhausted. The fix is to scale the pool or tune the query. After deploying the change, P95 latency drops back to 250 milliseconds. That's the trio in action. Put differently, metrics answer, is something wrong and how big is it? Traces answer, where is it happening along the request path? Logs answer, what exactly occurred at that point? This division of labor is simple enough to remember and powerful enough to use in the heat of an incident. Now, a few realistic limits shape how observability works in production. High cardinality data can explode storage and cost. Cardinality is the number of unique combinations of labels or fields. A metric labeled by region has low cardinality. A log field that includes user IDs and order IDs has very high cardinality. High cardinality isn't bad. Context is valuable, but at scale it adds up. Hundreds of thousands of unique log values or trace attributes can slow queries and raise bills. Sensible defaults help. Avoid stuffing long, unique strings into labels that drive storage, and prefer structured logs that separate message from context. Traces also add a bit of overhead. Creating spans and passing context takes a few microseconds and some bytes on the wire. For most services, that's negligible, but in ultra-latency sensitive paths or in partially instrumented systems, it can matter. That's where sampling enters the picture. Sampling means keeping a subset of traces or logs to strike a balance between cost and insight. For example, record 1% of all traces during normal operations, but record 100% when an error occurs. That way, the system captures every failure path in detail without storing every single success. It's another small piece of engineering elegance, selective retention focused on the moments that matter. Metrics have the opposite trade-off. They're efficient because they aggregate, but the cost of summarizing is losing per-request detail. Metrics can show that the average latency rose, but they can't show that 1% of requests hit a 10-second timeout in a specific service. That's why metrics are for detection and trending, while traces and logs handle diagnosis. A practical workflow tends to look like this. Alerts fire on metrics tied to user impact, latency percentiles, error rates, saturation on core resources. A runbook or habit steers responders into a trace view focused on the affected endpoint, time window, and a few key attributes like region or version. A suspect span is identified, perhaps a call from payments to inventory. Linked logs at that span reveal the reason: a timeout, a circuit breaker open, a database pool limit reached. From there, a fix is planned. Scale a pool, roll back a deploy, or ship a hotfix. The whole cycle aims to answer what changed, where it shows up, and why, in a calm and repeatable way. There's also a deeper shift worth noticing. Traditional monitoring leans on dashboards for predefined views. Observability values the ability to ask ad hoc questions without redeploying or manually adding new logs. If a novel symptom appears, say, only users on a specific device are slow, the system should support querying traces by client type, version, or feature flag. The tool here is not a static screen, but a queryable dataset designed to answer new questions. Engineering teams bake this into real systems in a few ways. OpenTelemetry SDKs are added to services so spans and metrics are emitted consistently. A service mesh or gateway helps propagate trace context by default, so cross-service calls aren't blind. Continuous delivery pipelines attach deploy metadata, build SHA, feature flag state, to spans, so new behavior can be correlated with code changes. And dashboards link to traces via exemplars, which are little IDs attached to metric points that jump straight to a representative trace. That small design touch connects the early warning world of metrics to the forensic world of tracing with a single click. And there's something quietly satisfying about that connection. Kubernetes environments add another layer of real-world integration. Pods, nodes, and containers are ephemeral, so labels like namespace, deployment, and version get attached to telemetry. That makes it possible to filter show slow traces from checkout service version 2.3 in US West during the last rollout. Teams that add this metadata early save themselves guesswork later. A common misconception is that more dashboards automatically mean better observability. Dashboards are great for known views, but they are not the whole story. The essence of observability is the ability to interrogate the system's outputs in flexible ways. If a brand new failure mode appears, predefined screens might not contain the lens needed. The ability to search logs, slice traces, and pivot metrics by novel attributes tends to matter more. Another misconception is that logs alone can carry the load. Logs are invaluable, but in distributed systems, sifting through logs without guidance is like reading every page of a novel to find one missing paragraph. Traces provide the table of contents for the specific request of interest. Metrics give the hint that this chapter even matters. Alerting strategy is another area where intention saves pain. Alerting on logs or individual trace events tends to backfire because there's too much noise. Metrics are stable for alerting because they smooth random blips and focus on user-facing signals. Error rate thresholds, latency SLOs, and saturation metrics are common triggers. When those go red, traces and logs become the microscope. This trio also affects how teams design code. High-value logs are structured and meaningful, not ad hoc print statements. Traces are named thoughtfully, so spans describe operations in domain terms. Reserve inventory instead of function call 17. Metrics match service-level objectives, so the numbers reflect what users feel. Naming clarity and a bit of consistency make incidents calmer because the telemetry reads like a story instead of a puzzle. So, how does all this prevent analysis paralysis? A simple mental checklist helps in the heat of the moment. Start at the macro level, metrics. Confirm there's a real user-impacting change. Move one layer down, traces. Isolate where the extra time or errors sit in the path. Finally, zoom into logs at that location for the concrete cause. That rhythm keeps attention disciplined and time-focused where it pays off. One more nuance makes a big difference: correlation keys. Attaching the same identifiers across logs, metrics, and traces, things like trace IDs, user IDs, order IDs, allows jumping between views fluidly. An alert showed a spike, click to a trace exemplar. Found a suspect span? Filter logs by trace ID. Need to understand if a deploy is involved? Filter spans by build SHA. This glue turns 3 separate tools into a single investigative surface. It's also helpful to think about costs and safeguards up front. Logs and traces can grow quickly. Guardrails keep the signal clear. Sampling is one lever for traces. Keep all errors, sample a fraction of successes. Retention policies are another. Store full fidelity data for a short window when it's most valuable, then keep aggregates for longer-term trends. For logs, limit high-cardinality fields in hot indexes, and keep verbose debug logs out of production paths unless actively debugging. For metrics, pick sensible aggregation intervals. 1-minute buckets are a common balance between resolution and cost. There's a humane side to observability as well. When a system tells its own story clearly, on-call work becomes less about scrambling and more about reading. A handful of well-placed measurements and traces can calm a chaotic incident. It is striking that such small bits of metadata, trace IDs, span names, a few labels, can pull clarity out of a very complex machine. The earlier analogy has a limitation worth calling out. A car's instrumentation is fixed by the manufacturer. Software doesn't come with gauges pre-installed. Teams add telemetry intentionally, service by service. In microservices environments where different languages and frameworks mix, that can be a journey. That's another reason open standards and shared practices matter. They reduce friction in getting consistent, correlated data. The moment when traces from a Go service line up cleanly with logs from a Java service and metrics from a C++ Edge proxy is a small triumph of engineering alignment. Where does this go beyond firefighting? Observability informs reliability goals. If a latency SLO is regularly violated at a specific span, that becomes a capacity or performance project. Traces reveal hotspots where time accumulates. Logs reveal error patterns that were previously background noise. Over time, dashboards can evolve to reflect the questions teams actually ask in incidents, not just generic CPU charts. That feedback loop is how observability shifts teams from reactive to proactive. Security and compliance benefit too. Detailed logs and traces support auditing sensitive flows like payments. Unusual patterns, sudden spikes from a specific client, or unexpected call paths can be spotted and investigated. Care is needed with personally identifiable information, but metadata that ties user actions to system behavior can be invaluable during investigations. Development velocity also improves when developers can run a trace locally or in a staging environment and see the same shape of spans as in production. It's easier to reason about performance implications before shipping. Feature flags can be attached to spans to compare behavior with a feature on or off. That closes the loop between code changes and user-visible outcomes. A final detail that many teams appreciate once it's in place. Context in the user interface. Linking metrics panels to trace searches and trace spans to related logs removes friction. One or two carefully placed links can save minutes repeatedly. Many platforms support this pattern now, and it tends to punch above its weight. It helps to return to the mental model one last time. Metrics are the gauges, compact, trend-friendly, great for alerting. Logs are the black box, rich, verbose, perfect for explaining specific events. Traces are the GPS. They map the route a request took through a maze of services. Each makes the others more useful. Metrics say, there is a slowdown in checkout. Traces say, the payment service waits on inventory. Logs say, the database pool ran out of connections. The combination tells the whole story, from symptom to location to cause. For those building or improving observability today, a few grounded habits go a long way. Emit metrics that reflect user experience, like latency percentiles and error rates. Name spans with domain language and propagate context reliably across service boundaries. Structure logs and include correlation IDs consistently. Use sampling to control volume without losing insight. And design for ad hoc questions, not just static dashboards. These aren't exotic techniques. They're the basics that unlock fast, confident diagnosis. One last appreciation before closing. It's easy to take telemetry for granted, but consider the odds it works at all. A single request can cross dozens of processes and networks, yet a small thread of identifiers keeps the story intact. A handful of percentiles and counters can warn of trouble, even when billions of events flow by. That quiet precision is an under-celebrated part of modern software's reliability. So the next time that checkout slows down, the path forward doesn't have to be guesswork. The gauges reveal a spike, the route shows where it happened, and the black box explains why. That's observability in practice, turning opaque complexity into understandable signals that lead to action. If this helped, a like and subscribe helps more videos like this reach the right people.